name is Ava Martina, and I will be presenting on Lab 1 of Physics 2211. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. I will analyze the marker's motion and create a computational model in GlowScript based on the data we collected and compare both data. Finally, I will address the questions, what if and what does it mean in the discussion portion. The purpose of this lab is to observe the motion of an object moving at a constant speed without changing direction. We will compare this measured data with our predictions made in GlowScript. To give a quick preview, we will find that no external forces are acting on the marker, which indicates that there is no acceleration and a constant velocity is maintained through the experiment. In this scenario, our marker is our system, while everything beyond the marker, such as the table and the air, constitutes our surroundings. Some important concepts we use include Newton's first law, which states that an object in motion stays in motion unless acted upon by an external force, and Newton's second law, which states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Additionally, we utilize the position update and velocity update formulas, which you can see at the bottom. It is also important to note that Fnet should equal 0 to ensure that there is a constant velocity and no acceleration and friction are acting on the system. Here is a video of our marker and tracker data. If you examine the position versus time graph here, you will see that there is a positive slope. This indicates that the marker rolled from left to right. You will also notice that it's linear, meaning that it is moving at a constant velocity. In GlowScript, I first set the marker's mass to be about 1 gram, then updated its initial position to be 0.958 on the x-axis and its velocity to match our data from Tracker. Our delta t was found between our first and second data points, from 0 to 0.033 seconds. I kept the time interval of the computational model within the delta t used from the experiment. I also kept the net force as 0 to ensure that the velocity is constant. Under Newton's second law, also called the momentum principle, I used the velocity update formula, which is initial velocity plus Fnet divided by the marker mass times delta t. Because there is no net force, the Fnet vector would just be 0. The position update formula is initial position plus the average velocity of the marker times delta t. When comparing the graphs from the computational model and the experimental data, both show linear positive trends. However, there is a small deviation at the end of the experimental graph, likely caused by the negligible friction force of the table. Now, what if the axes were flipped? If the marker had rolled from right to left instead of left to right, the graph would be reflected over the x-axis, as seen on the left. However, this would not change the results from the experiment, because the marker would still be rolling at a constant velocity but in the negative x direction instead of positive x direction. Can we determine the net forces acting on the marker? We cannot assume that the net force is 0 because of the external force such as air resistance, gravity, and friction acting on our system. In our computational data, however, we were able to set the net force equal to 0, which is why the computational graph, compared to the observed graph, was more linear. Due to the slight bumps and curves in the graphs, we can conclude that some small external forces were indeed acting on the marker that we could not see.